let's talk about nets. First of all, you have to understand that these tumors are classified by pathologists, basically. Now, there are a couple of things you need to know about a pathologist that nobody gets out alive in a pathology lab. That's the first thing. So, you take these tumors and you look at them by the degree of differentiation. Now, what's a differentiation? It means how much do you look like your sisters and brothers? How much does this tumor look like the normal cell it arose from? And then the location of the primary lesion. And it's very important because lung nodes are different than thymic nodes, and pancreatic islet cell tumors are different than duodenal islet cell tumors, and both of those are different than rectal carcinoids. The NETS docs like the concept that tumors are classified not only by their differentiation and location, but by their functional nature. And Dr. Werner was telling you about that. In other words, things like carcinoid syndrome define whether something is functional. Does your tumor make something, and does it, more importantly, release that something into the blood? And the secretion is what's critical, not the fact that it's inside the tumor. Well, let's look at some examples of the problem. You have a bronchial tumor. It's well differentiated, or moderately well differentiated, or poorly differentiated. And then you have a pancreatic tumor that's well differentiated, moderately well differentiated, and poorly differentiated. But the problem is that makes a pathologist smile from ear to ear. It's told you where it is, and he told you how well it's defined. And it takes somebody like me, or Dr. Warner, or Dr. Odoricio, or Dr. Oberg, and we go, but, what does it make? Because what it makes is what's going to make you sick in many cases. Is it in the urine? Is it in the blood? Is it in saliva? How do we measure it? What do we measure? Well, there's no official kind of staging system. Now, staging is different than pathologic classification. Pathologic classification is where is it, how well differentiated is it. Staging is how much of it is there. And those people who do the cancer field sort of look at it as you got a little bit, plus you got some lymph node involvement, you got the primary and a whole bunch of lymph node involvement, and then you have distant disease. So stage 1 means you have a relatively small tumor. Stage 2 means you have a larger primary tumor. Stage 3 means you have a primary tumor plus lymph node metastasis. And stage 4 means you have evidence of widespread disease or an organ met like lung, liver, bone, brain. Now, this is not an official kind of thing. It's just sort of how I classify things in my mind. So I sort of know, do I have to bring out the big guns now, or do I have the little guns that I can do? Where your metastases are and where your primary tumor is can be really critical. In other words, let's talk about somebody who has a lung node or a woman who has a carcinoid of the ovary versus somebody who has a carcinoid of the bowel. The bowel, let's say it's a functional tumor and it secretes serotonin. The serotonin gets into the portal vein, goes to the liver, and the liver gobbles it all up, and you don't have syndrome. But if you have the ovary or you have a lung, the first place that it drops into is the vein, and the veins go to the heart shoots it out to the lungs, back to the heart, and out to the whole body, and then finally to the liver. So you can have syndrome with just a primary tumor of the lung or the thymus or the ovary, where if it's gut-based, you have to have metastasis of the liver, essentially, to have syndrome. For islet cell tumors of any location, you can have full-blown tumor with stage 1 disease. Okay? Why? Because some of it can escape through other sort of pathways. Well, there are two kinds of nets in my humble opinion. There are carcinoids and there are islet cells. Now, that's a gross simplification. There are tumors of the thyroid, tumors of the adrenal, tumors that Sue Odoricio will talk about, neuroblastomas and stuff of the sympathetic nerve root. But you basically have these kind of carcinoids, and if they're functional, they're going to be secreting amines like serotonin, and islet cell tumors that make peptides by and large, and then non-functional tumors that can straddle the fence. Okay. Oops. Well, how would I classify your tumor? Well, I would first look at it and I'd ask the question how well differentiated it is. Is it moderately well differentiated? Is it poorly differentiated? And that, to me, tells me the first inkling, because the better differentiated you are, the more you look like your parents and your brothers and sisters, the better your behavior. Then I would look at location, and location would be pancreas or ileum or right adrenal. And I know that there's some bad versus good locations. Dr. Warner was talking about it. Appendix. A much more ho-hum tumor than a thymic carcinoid, which are very rare, but usually much more aggressive. And then finally, I would be looking at the tumor's secretory nature. If it's carcinoid, I'd be looking for flushing, diarrhea, pellagra, all the things that Richard talked about. If it was an insulinoma, I'd be looking for changes in your blood glucose and the fact that when you don't eat for a while, you fall out because your blood sugar is so low. Or a pheochromocytoma, which is an adrenal tumor that blows the top off of your blood pressure and gives people these feelings like, I'm gonna die. And then how do you find which of these it is? How do you sort that out? Well, that's where the blood test, the urine test, and the scans, etc., all come together. Well, let's just run through some of the islet cell type tumors now, please. Again, we know that there is, in the grand scheme of things, a lot of different ways to look at these, but these are how I'm doing it. Islet cell tumors, and if they're functional, they can make insulin, that lowers your blood sugar, and it's balanced out. Everything in nature, and Dr. Odoricio was the one who really taught me this. There's a yin and a yang. Everything in God's green earth is balanced out on one side by insulin that makes your blood sugar go down, and on the other side, something that makes your blood sugar go up, like glucagon, growth hormone, or even some things called pancreastatin. Glucagon and insulin are the opposite. So if you have an insulin-producing tumor, you have low blood sugar. If you have a glucagon-producing tumor, you have higher blood sugar. But it is also balanced out on that teeter-totter of life. If you're over-secreting glucagon and your blood sugar is going up, now you can secrete more insulin and balance everything out. I have one patient that I saw when I was in Oregon who had 5 different peptides that were off the top of the chart, numbers-wise. But they all sort of balanced one another out. One caused acid secretion in the stomach, the other one blocked acid secretion in the stomach. And the net was the guy was asymptomatic, even though he hyper-secreted a whole bunch of peptides. Gastrin makes acid, VIP makes your stomach acid go down, so if you had a bunch of VIP and a bunch of gastrin, you may have absolutely no ulcer disease. And then somatostatin is our friend. It is, as I call it, the universal off switch. If you were God and you were designing the perfect counter-regulatory off switch, it would be somatostatin. You eat breakfast this morning, your blood sugar goes up, you secrete insulin. Everybody who's normal here in their insulin secretion secretes insulin in a response to blood sugar. But then your blood sugar goes away. What turns off insulin in you or me is somatostatin. But it turns off everything. It turns off glucagon. It turns off growth hormone. It turns off serotonin. And it not only does those things at the level of the tumor cell, Somatostatin also works at the end organ of response. Okay? Example, got a gun. Bang. This is where the bullet's fired. Unless I'm a CSI, do I really care? What I care about is who do I kill with that bullet. That's the end organ of response. So somatostatin blocks the ability to fire the bullet. But just as importantly, it's the bulletproof glass in front of the guy who's giving the lecture. Where'd they go? Okay, how do peptides work? Well, traditionally, peptides bind to a receptor. The more peptide, the more receptors that are occupied. The less peptides, the fewer receptors that are occupied. And it's sort of like walking up to a room, opening the door a little bit, and sticking your hand in and flipping the light switch on or off before you walk into the room. Peptides act by opening the door. And then next action is they flip on and off the light switch. And that's something, called the G protein. And it acts like a translator program or your hand toggling on and off the light switch. The G proteins then turn on and off signal transduction pathways. What the hell is a signal transduction pathway? Because you're going to hear a whole bunch about signal transduction pathways because we're developing drugs now that block specific pathways. Notch pathways. Dr. Chen, you'll hear talk about that, valproic acid. You'll hear about RAD001 and the mTOR pathway. And then there's plain old somatostatin analogs like octreotide and lanreotide that act through this G protein and calcium IP3 and cyclic AMP. Our group was one of the first to show that many of these peptides can translate to the nucleus, and it may well be that peptides have two different actions. One that's receptor-based, and then once the peptide gets into the cell and gets to the nucleus, it may act in a totally different way. And here's a picture of a neuroendocrine cell, and you can see that we've radio-labeled a fluorescently labeled a somatostatin analog, and then continuously exposed these cells to that fluorescent analog for 72 hours, and then washed all the fluorescence off and let it sit for a while. And you can see that it went right to the nucleus of the cell. Well, how do amines, the opposite guys, the serotonin kind of guys? If you've ever known anybody who's depressed, they talk about a class of drugs called SSRIs. And those are serotonin reuptake inhibitors. And serotonin is one of these neurotransmitters. Serotonin, histamine, bradykinin, epinephrine, norepinephrine, or adrenaline, norepinephrine. And then there's this sort of crossover. He's the utility player. VIP can come from an islet cell tumor and act like a neurotransmitter, as well as to act like a peptide to cause diarrhea. In general, these don't cross the blood-brain barrier. So if you make 8.5 tons of serotonin, you flush like a madman, you have atomic diarrhea that lifts you off of the toilet, that serotonin still doesn't get into your brain and make you less depressed, unfortunately or fortunately. How do peptides and amines work? Well, they work by binding to a receptor. It's the same concept of both. If the concentration of the peptide or amine goes up, there are more binding to the receptor. If it goes down, it also binds. The whole effect of peptides and amines have to do with time on the receptor and the number of receptors filled up. And that's important because that's why the same number of micrograms of octreotide given by pump is far more effective than given into 2 once every 12-hour boluses of sub-Q. In those cases, you're loading up receptors and then they quickly unload versus a pump that keeps everything loaded all the time. Well, I'll give you an example. This is also true we found with radioactive stuff. And what we did was, and it's hard to see, but basically we had increasing amounts of radioactivity. And I'll show you people over here. Increasing amounts of radioactivity. And how we got those numbers were the amount of stuff versus the time. And so you could use a short time with a lot of stuff, or less stuff with longer time, and all get the same thing. But the bottom line is, no matter how you mixed it up, high amount, short time, high, or a long time, short amount, the effect was basically the same. And it is the product of time and concentration of the drug that makes the big difference over time. It's very simple. It's the more dose you have, the more it goes up, the more time, the more it goes up. Well, what about the syndromes? Insulinoma, we talked about it. How do you diagnose this? It's a 72-hour fast, and you measure insulin, C-peptide, and glucose whenever you get symptomatic. How do you localize these things? In the case of insulinoma, it's the one thing that we don't really recommend Octria scans for. It's something that we do endoscopic ultrasounds, we do intraoperative ultrasounds, CAT scans, MRI scans, and even arteriography with stimulators, but Octria scan is not real helpful. Gastronoma, it is the best thing that you can do an Octria scan for somebody with a gastronoma. It is the most sensitive of all the neuroendocrine tumors for being picked up on an Octria scan. How do you know you got a gastronoma? Well, it's the syndrome of ulcer disease and diarrhea. And how do you diagnose it? By high gastrin levels, chromogranins. But the most important thing is, if you have Zollinger-Ellison syndrome or a gastronoma, you have to make acid. You can have a gastrin level that is sky high in a disease called pernicious anemia. And in pernicious anemia, or type 1 gastric carcinoid, your stomach has no acid, none whatsoever. And the high gastrin is a response, a natural response to no acid. Vipoma, how do you know you have it? Again, profuse watery diarrhea, up to 10 or 12 liters per day. Tom Motoricio, again, one of my long-term friends, was the first person in North America to use octreotide. And he used it in a gentleman who had a vipoma, and this poor son of a gun couldn't get out of the hospital. Odo gave him octreotide, and within a week, the guy was back home, and he lived for years and years and years and years, decades, I believe, very well controlled on octreotide, where before he couldn't get out of the hospital because he was making 3 or 4 gallons of stool per day. And you just couldn't keep up with those kind of losses. Glucagonoma, migratory rash, diabetes, and the key one is thrombosis of a major vessel. How do you diagnose it? By elevated glucagon levels. How do you localize it? By the traditional octreotide and CT scans. Somatostatinomas, while somatostatin is the perfect control substance if you're the divine being designing a human being, if you have a tumor that overproduces somatostatin, it is a booger to make that diagnosis, because everything that it creates is just a mild change. If you have diabetes, it's mild diabetes. If you have gallstones, it's sort of like, so does Aunt Minnie and Uncle Fred, and they don't have somatostatinomas. And the diarrhea that you have is an unusual kind of diarrhea called steatorrhea, or the dreaded floaties, if you've ever heard me talking about those online. The other one is carcinoid syndrome. We've talked about it a lot. How do we localize these tumors? Octria scans, CT scans. You can then do things like MIBG scans. If you're Dr. Oberg, you can do very super duper specialized scans. that are called PET scans, but not the kind of PET scans that we use in the United States, which are called F18 fluorodeoxyglucose, not radioactive glucose. He makes a PET scan that is very unique and the only place in the world that can do it, but it's incredibly sensitive. Well, what biomarkers should we be using? Well, we reviewed 8 consensus papers. We wanted to know which biomarkers were recommended, and remember that the markers need to be measured for MEN1 and MEN2, as well as the primary diagnosis. In other words, there are tumors, especially those islet cell tumors, that are associated with other tumors. I'll give you an example. Gastronoma can be associated with pituitary tumors and parathyroid tumors. If you have a pituitary, a parathyroid, and a gastronoma, you probably have MEN1 syndrome. But you need to measure this and this, as well as the gastrin from this. And these are the 8 papers that we looked at. They're in your list. And the bottom line is let's look at who recommends what. And essentially, every single one of the consensus papers say whether you're an islet cell or a carcinoid, you need to have chromogranin measured. Very few people measure things like substance P or neurokinin. And for the carcinoids, not the islet cells, 5-HIA is mandatory. If you're an islet cell type tumor, people have what's called a peptide profile, and that is gastrin, pancreatic polypeptide, insulin, VIP, glucagon, and somatostatin. And if you have things like the MEN, you want to measure parathyroid and things like your pituitary hormones, like growth hormone. And I think the quick and dirty ways to remember, for carcinoid, you measure CGA 5-HIA, and Dr. Odo's going to talk, I hope, a little bit today about pancreastatin, a new marker that we think is the hot ticket. For islet cells, you do a whole big panel, and then you just follow what's elevated. And finally, remember that trends are really the way to be a predictor. If you have 3 people who have, let's say, elevated gastrin, one with a gastrin of 300, one with a gastrin of 3,000, and the other one with a gastrin of 30,000, who's in trouble? Well, the logic would be it's the guy with 30,000. No, it's the guy who went 30, 60, 90, 120, 150, 200, 300, rather than the guy with 30,000 who's had a gastrin of 30,000 for 10 years. Thank you very much. We'll stop there.